dielectric constant of water change becomes more organic in nature, it can corrode diamond. Once the diamond is below the graphene. Diamond is well known to be highly corrosion resistance. That's what diamond is famous for. Very hard and corrosion resistant. You want to corrode diamond, you normally have to use very adverse extreme condition. You have to use catalysts, you have to use very strong condition. But water corroding diamond, I think this is the first time people report such a thing. It is quite incredible. Now the water that's trapped within the bubbles, they become supercritical and they start to corrode the diamond. So we can form these pits. Diamond becomes corroded. This gives us a clue. If you perform hydrothermal chemistry using water at high pressure and high temperature, maybe you can corrode diamond. But nonetheless, what is the pressure that's inside the bubble? Normally diamond can be corroded if the pressure is very high, megapascal, hundreds of megapascal and above. According to simple calculation, there's a, if you do a simple calculation based on the fact that you have to strain the graphene to form a curvature like this, you can calculate how much pressure is needed. It's almost gigapascal range. So we guess the pressure inside this tiny bubble is gigapascal. But what is the proof? How do we measure the pressure inside a nano bubble? Any physics instrument that has such high sensitivity allowing us to probe what's the pressure inside? As I'm not a physicist, I do not know how to use an instrument to measure the pressure, but we can use chemical molecules to calibrate the pressure. Chemical molecules, some chemical molecules are twisted. You see this carbon ring, this 6-membered ring, this ring, they are sort of twisted. It is known by theoretical consideration that if you want to bend the ring and make it flat, you need a certain pressure. This pressure can be as high as megapascal or gigapascal. So the experiment is very simple. These molecules show the infrared active vibrational modes when it's twisted out plane. The moment you bend it in plane, these IR active modes will disappear. So I just need to put these molecules inside the bubble, heat up the bubble and see when does the infrared active modes disappear. At the point where it disappears, it must have a certain pressure inside the bubble. So this is the experiment. True enough, we put these molecules inside the bubble and then we perform FTIR experiment to monitor when does the peak disappear. We do not have to worry about all these peaks. You just see that initially at 25 degrees Celsius, we can track the vibrational modes of this, what we call the biphenyl molecule, the twisted phenyl ring. The moment we heat it up to 500 degrees Celsius, okay, the ring did not disappear until 500 degrees Celsius. Then you see immediately that this peak disappear. And then if you cool it down back to 25 degrees Celsius, it comes back up. So the process is dynamic. So using this chemical molecule, we have a biphenyl, triphenyl, tertiary phenyl. The longer this molecule, the harder to bend all the ring back in plane. And then performing a theoretical calculation to know what is pressure needed to bend it in plane. We can calibrate the temperature and pressure relationship. Okay, so now we know when we heat up to about 100 degrees Celsius, the pressure inside the bubble is about 0.3, 200 is about 0.5, and so on. Once you exceed, once you go beyond 400 degrees Celsius, you're already in a gigapascal regime for the nanobubble. The pressure inside is as high as gigapascal, which means that it's a totally different regime from what we are experiencing normally. You can perform chemistry that's normally you don't perform using the test tube and beakers. This is high pressure, high temperature chemistry. To prove this further, we can put fluorine molecules, C60. It's well known in chemistry that if you want two C60 molecules to bond, intermolecular bonding, force them to bond, the soccer ball, they are so stable that they don't like to form bond. This intermolecular bonding between a C60 is forbidden, symmetry forbidden in chemistry. Chemistry, we call this the 2+2 cycloaddition of C60, symmetry forbidden due to the mismatch of molecular orbitals. However, under high pressure regime, this rule does not apply. Most of the chemistry rule is derived at normal condition, atmospheric condition. Under high pressure regime, you force the molecule to come very close. They have no choice but to form bond. And when they form bond, the C60 molecules will polymerize. C60 will join. From two C60 come together, they form a dimer, they form a trimer, they form a tetramer. You get a oligomerization, or what we call the polymerization of these C60 molecules. And you can track this using, again, FTIR, pristine C60 molecules, because highly symmetrical, you see 4 peaks. The moment you put it inside the bubble and start heating up, new peaks appear, which we can assign to the various different phase because of the oligomerization of these C60 molecules to become a dimer, tetramer, and so on. And the phase transition is very sharp. From 1 C60 to 2 C60 to 3 C60 joining up, it's a very sharp phase transition. Now, this work has been accepted in Anguan chemie. Now, very interesting effect of these bubbles. The next question is there any technological applications which is meaningful for these graphene nanobubbles? From my research, I found 2 effects. One is optical effect. The other one is a surface tension effect. Optical effect. Normally, when you have flat graphene and you shine light perpendicular to it, or if you have the graphene vertical and you shine light along plane of graphene, the light matter interaction will be different. Now, for flat graphene, because it's so thin, there's very limited absorptive path length. You cannot expect the graphene to change the optical path of the light. It's only one atomic layer. But once you form bubbles, you have extra vertical sidewall, which is in the vertical dimension, so you increase light matter interaction. In fact, this graphene is a very interesting photonic material because of 2 effects. One effect is the saturable absorption. Now, when you increase the laser intensity on the graphene, initially absorb the light. At some point, the absorption becomes saturated because of the Pauli blocking, and then the material becomes like transparent. Okay, so you have the absorptive state with opaque to the transparent state. This can be used as a basis of optical bistability. Another effect is the optical K effect. Now, this material can have intensity-dependent refractive index change. Okay, this second effect is useful also in optical bistability. So what we do is that we set up this Fabry-Perot cavity. We build it ourselves. In the Fabry-Perot cavity interferometer, you have 2 mirrors, and then you have light going in, focus through a lens, light going in. Undergo internal reflection. When there's constructive interference, because it satisfies the dimension between the mirrors, it satisfies the wavelength or refractive index, you get this constructive fringes that you can see. Now, once you put graphene inside, you find that it can change optical path by lambda O2. Now, this is a 532 nanometer light single mode laser. Lambda O2 corresponds to 266 nanometer. You can change the optical path length by 266 nanometer. It's impossible for a single layer graphene which is flat, you see, because the absorptive path length is too short. Because under the intense laser irradiation, it starts to form bubbles on the graphene, and with the additional vertical sidewall, it has a dispersive interaction. Then it gives rise to this optical bistability. Without the graphene, input power, output power is linear. Once you put the graphene in, you get a hysteresis. Now, this is the characteristic of optical bistability. Once you put 1 input power, you can get 2 output power at resonance. Now, this is very useful as a basis of optical switch, you see. So, it's a very interesting effect. Now, if we can compare monolayer graphene and bilayer graphene as well. The green line corresponds to monolayer graphene. Bilayer graphene is 2 times. The bilayer graphene has a nonlinear, the refractive index is twice that of the monolayer graphene. So we only need to use half the switching power to achieve resonance, at the same cavity detail. And the bilayer graphene absorbs twice the amount of light compared to monolayer graphene. As a result, you find that output power in bilayer graphene is half, you see, because monolayer graphene absorbs less light, so the optical cavity has a higher optical intensity. So it's very interesting proof that just by changing the thickness of the graphene, you have this very interesting variation. Another interesting application which we just published in Nature is the fact that the bubbles have very serious implication in the absorption of a film on the surface. You see, you remember that if you put a plastic sheet on the table and then you have water going in between the plastic sheet and the table, you find that this plastic sheet can stick much better. It is not because water is very sticky, right? Because if you dip the whole thing into a deep pure water, the plastic sheet will just come off. It is because of the air-water interface. At the air-water interface, there's a curvature, and this causes the capillary adhesion force. The same applies to the bubbles. When you are able to engineer the bubbles between the graphene and a certain substrate, these bubbles, because of air-water interface, allow the graphene to stick to the substrate very well. This is the basis of our technology to grow and transfer graphene on silicon wafer. Okay, the product, this graphene on silicon wafer is a technological breakthrough, because normally, currently, everybody grows graphene on a copper foil, and they actually with a copper foil. It's very difficult to grow on silicon, because silicon is lattice mismatch to graphene. But you can actually have copper on the silicon wafer, and you grow the graphene on the copper first. This is illustrated here by the diagram. We first, this is silicon oxide. Normally, this is what we do. We use a nitrogen plasma to engineer trap gas within, and then we sputter the copper, which is the catalyst, and then we grow the graphene on the copper. And by some treatment, the bubbles start to appear from the substrate, and then these bubbles will merge to form a capillary bridge, so that when the action solution come in, it removes the copper catalyst. Although there's water in between the graphene and the substrate, the graphene did not delaminate, it still remain attached because of these bubbles holding the thing together. This is the capillary bridge. And subsequently, when you undergo a baking, then the graphene will just stick onto the wafer. So this allows us a very good way. We call this the face-to-face transfer of graphene film, and because this is a technological breakthrough, it has been published in Nature. The biomimetic model of this is that you have an insect. Normally, you have an insect. If you look at the legs of the insect, it sticks on a leaf. You put the, this leaf, lotus leaf can be submerged in the water, but the legs of the insect remain bound on the lotus leaf. You did not leave the lotus leaf, even though this is submerged in the water. The reason is this, because the legs of the insects, there are many trapped bubbles, because the insects have very heavy legs. And then they have trapped bubbles, and these bubbles generate the capillary adhesion force. Again, because of the curvature between the air-water interface. It's the same principle that we apply here. So this transfer process allows us to grow large-scale 8-inch graphene wafer on silicon, and we can pattern very long lines, lines that are millimeter to centimeter long, and we find that the conductance is very good from this face-to-face transfer process. Wes, do you have any time? So the next part, I will talk about another type of defective graphene. We call this the graphene oxide. That's the thing that's interesting to the chemist, maybe not interesting to physicists, but I share with you because this is very important for the chemical technology, how to generate defects on graphene. Recently, I published a work called Probing the Catalytic Activity of Graphene Oxide and its Origin. So, the chemists, they like to use catalysts to catalyze reaction. When you have a certain chemical reaction, A plus B equal to C, normally there's an activation barrier. If you do not lower the activation barrier, it takes a long time to finish the reaction. And you have to increase a lot of heat or apply energy or pressure to accomplish this reaction. Now, use catalysts, you can get a better efficiency. And it just happens that graphene oxide can be a very good catalyst. It can catalyze organic transformation. How is it possible? So I will show you how we investigate the origin of catalysis in this material. Now, graphene oxide is just like graphene, except that it has a lot of oxygen functional group attached to it. This oxygen functional group can be different type. It can be a carboxylic acid, COOH. This makes it acidic. Or it can be an epoxy group as well as a hydroxy group at OH, you see. Now, a COOH group makes this material becoming an acid. Now, this material has acidic property because it can undergo protonation and deprotonation. The hydrogen can be deprotonated or protonated. Once it's deprotonated, you get a carboxylate CO minus with a counter charge of sodium plus. So this is interesting because it means that the material can undergo ionic interaction. And with all these oxygen functional group, it becomes a handler for performing different type of chemistry. It can be oxidant, because some of the oxygen group can be supplied to a chemical reaction. It becomes an oxidant. It becomes an acid because they can undergo protonation and deprotonation. It can react with a base like amine and so on. The graphene oxide is very hydrophilic because of this oxygen group. This oxygen group is ionic, hydrophilic, meaning it loves water. So recently we did an interesting work. Graphite is hydrophobic. Everybody knows graphite is hydrophobic. It doesn't like water. And can you grow ice on graphite at room temperature? It's probably very difficult. do is, we seed the graphite with a little bit of graphene oxide, very small, nanoscale graphene oxide. Just sprinkle a little bit of nanoscale graphene oxide on graphite. And you'll find that it's able to condense water. You form a one-dimensional ice, you get nanocrystal ice. First, the graphene oxide will undergo self-assembly because of hydrogen bonding. You can form a one-dimensional graphene oxide lines, you know. And once this line forms, it guides the ice nucleation. You get a plate of ice. See, all these are ice. At room temperature, you can actually get ice nucleation on graphite just by a sprinkle, 1% surface coverage of nanographene oxide, because the material is highly hydrophilic. So do not underestimate. The message is, don't underestimate these messy things, because these fragments of flakes, these are small flake, micron, sub-micron size flake, a lot of oxygen functional group, super hydrophilic. It's a very strange property. Okay. So this is room temperature ice growth. You can refer to this paper, which is published in Underwater Chemie. This comes as the cover page in Underwater Chemie. What is the hotspot for catalytic reaction? The perfect graphene is useless for chemists. Totally useless material. It's good for physicists, but when the chemists look at this, they find very boring. They're nothing, very flat. The chemists like to destroy it by introducing all kinds of functional group. Okay, you destroy the thing, destroy it by introducing functional group. Then this becomes a very interesting material. Hotspot for catalytic reaction. For example, you introduce this kind of a functional group. We call this the diketone. It can be used in the oxidative dehydrogenation of some ethyl benzene to form the styrene, which is very important for forming the plastic and so on. You know, you can also introduce nitrogen groups, you know, things like that. Sometimes you generate some unpacked spin, you know, then it gives rise to the possibility of a spin flip process in catalytic reaction. All kinds of strange things is possible. Okay, so there's solid acid possible if you introduce this sort of functional group, and all this oxygen group can be oxidative in nature, and then you have redox active site because you can perform redox exchange. All these imperfections help to mediate its catalytic properties. This is the key message. So what we do is this. We synthesize the graphene oxide by the usual Hammers method, and it produces graphene oxide, which all kinds of functional group. The question is, which one is responsible for the catalysis? You know, how do we know which one is useful? Maybe some is useless. Now, what we do is we do a base reduction. It happens that during the oxidative treatment of graphene oxide, you actually generate a lot of small fragments. It's oxidative debris, small fragments. This oxidative debris is super hydrophilic, has a lot of oxygen functional group. We have to do a base reduction to wash away this oxidative debris. Otherwise, you coat the entire graphene oxide, give it a very high oxygen content, but actually it's not due to the graphene, but it's due to this oxidative debris. You do a base reduction, remove it, and do a neutralization, regenerate a very potent material. Now, this material is highly, we call this the base acid graphene oxide. Base treatment followed by acid treatment, graphene oxide, we call it BAGO. We have made a patent on this. These are very highly active catalytic material. And we do analysis to find whether there's any metal impurities. After the base acid treatment, it can be seen that the manganese. This manganese is important because we use potassium permanganate in oxidation processes. Manganese is reduced to less than 1 part per million, even less than original graphite. And iron, zinc, gold, ruthenium, all the magnetic sort of metal or non-magnetic metal is reduced to very low concentration. So it's the catalytic property is not due to the metal. We use this chemical reaction. Excuse me if it bored, if you're not familiar, but basically this chemical reaction is a classic reaction just to show how we can couple this. We call this a benzoamine. We use a BAGO as a catalyst. This molecule couple, it forms this. We call it N-benzylbenzidamine. In this kind of a chemical reaction, it's an ideal model. We don't need any solvent, solvent-free. We only need to use BAGO and the reactant. Solvent-free, only reactant. Open air, safe. We do not need to use high pressurized oxygen, just air. Low catalyst loading, just a little bit, just about 5% weight loading of BAGO. We can achieve very high catalytic efficiency, about 90% yield of the product with very good recyclability. So this BAGO is a low-cost, non-polluting, and reusable catalyst compared to gold on carbon. Now, normally, for the same reaction, you carry out using gold on carbon. They have to support the gold on carbon. They don't just disperse gold in a solution. You cannot recover. So the gold has to be supported on carbon. And the amount of carbon that they use is a lot for the conventional catalysis. The total catalyst loading is 250 weight%. In this case, we do not need to use gold. We just use the BaGO, which is graphene oxide, no gold, just this alone. And the catalyst loading is only 5 weight%. And you compare the price versus gold, compare the oxidant, we use open air. For this reaction that the chemists normally use 5 bar molecular oxygen, pressurized oxygen to catalyze. And they need to use solvent. Reusability is not very good. The yield is not good. Here is good use. We can use up to 6 reuse because we tested up to the 6th cycle. It's very good. So it seems like the graphene oxide itself, the carbon material with oxygen group, can behave as a catalyst, even compared to metal. Then the question is, how come? Why? Now, then we have to look carefully at this material. What happened during the chemical treatment? Well, this material is a crappy, defective material that the physicists will not want to take a look. But you see, because after the chemical treatment, it's highly porous, all the holes, defects have been generated, all kinds of holes. The more holes, the better for the catalysis, because the holes are where all the dangling bonds and pad spins are all how we know. We performed the electron spin resonance study. At the edges of these holes, maybe they have the non-bonded pi electrons. The non-bonded pi electrons, dangling bonds, untapped electrons, highly reactive at the edge. Because if you perform electron spin resonance on a normal graphene oxide, which has not been subjected to the same treatment, we see a very sharp signal. And this is according to the carbon researcher who are familiar with the ESR, electron spin resonance. They've been studying this for the last 30 years on carbon materials. This kind of a signal is characteristic of the sigma bonding, non-bonded sigma bonded type electron. But after we subject our graphene oxide to the treatment, we generate lots of holes. We see a second peak, a broader peak, which is assigned conventionally to the edge spin, the spin that's at the edge. Because of very fast spin lattice relaxation, these electrons are delocalized along the edges, causing this much broader EPR signal. Now this is very important, this H spin. If we do a chemical reaction to quench the H spin, which we can do, we add some chemical molecule. There's a diazonium coupling reaction. The organic molecule go to the H, quench this H spin, then we find the catalysis is the U is quenched. Now once you quench the H spin, you don't see it, it becomes very sharp. So this H spin, due to these defects, they are very important for the catalysis, the H spin. Again, and at the same time, the carboxylic group, COOH, this group COOH, for people that are familiar with chemistry, if you take an aromatic platform, and I say transform one carbon to COOH, you find that you can't do it, you see. You can transform to COH or 2 carbon with an epoxy group, but to make a C carbonyl O, C, and then with the OH, you cannot at the basal plane. You can only do it for the H carbon. So the COOH can only exist at the H and not on the basal plane, only at the H. And the COOH group is also very important. We can prove this by FTIR spectroscopy. Now, if you get a graphene oxide, you can see this COOH, this COOH group. The moment you react with a base, the base will transform the COOH to a carboxylate, CO minus Na plus. Once you transform to a carboxylate with a proton disappear, straight away this peak disappear, you find that the catalytic U decline dramatically. Then you have to do a base neutralization. You introduce an acid again, so you have carboxyl recovery. Then your catalytic U improve. This tells us that you need the carboxylic group to be COOH and not COO minus. So this COH group is very important. Okay, if you neutralize it with a base, form the CO minus Na plus, it's not going to work. So the synergistic effect of the acidic group and the spin is responsible for the catalytic reaction. We can follow this reaction using the DMPO spin trap EPR spectra. We can trap some of you introduce oxygen molecule. The oxygen molecule is activated by this kind of dangling bonds and the carboxylic group structure. It's activated to form a superoxide, which can be trapped and detected an EPR signal. there's no catalyst, you don't see this. Anyway, this just show you that the synergistic interaction of the acidic group and the spin give rise to a very high catalytic activity. So the conclusion here is this. Strange structures like graphene bubbles afford a new energy landscape. Which you strain the graphene, you change the energy landscape completely, you open up a band gap. The graphene bubbles can be used as a hydrothermal cell for studying reaction dynamics at high pressure and temperature. This is very interesting. Now the chemists, we are stretching our head to see what kind of new chemistry we can uncover in this condition. And the defective, the more defects, the better. Porous graphene oxide can be effective catalyst. It's a new term we call the carbo-catalyst, the carbon catalyst. The carbon catalyst may be very good. It can replace all the expensive platinum metal catalysts, for example. Okay? And most of the work that I described here has been published in this series of Nature paper. For example, we have studied the transformation of fluorine molecules into graphene quantum dots that's published in Nature Nanotechnology. We have explored the use of graphene as a broadband polarizer in optics that's published in Nature Photonics. Today I discussed the transformation of graphene Moray blisters into geometric nanobubbles that's published in Nature Communication, and the catalytic activity of graphene oxide also published in Nature Communication. The hydrothermal induced cell make of graphene nanobubbles on diamond is also recently published in Nature Communication. Thank you very much.
Okay, now it's open for questions. Yeah, please.
And session 2 of part 1, how do strength of the bubbles influence the peak shift of the IDV curve?
You mean the DI? You mean the scanning tunneling spectroscopy curve that we observe? So the higher the strain field, the larger the cause of splitting of this energy level. The energy level is split, you see. Once split to higher energy levels, the separation between energy levels becomes wider and wider with a larger strain. It generates a larger pseudomagnetic field that split the energy level. The bigger the magnetic field that you apply, the more you split these energy levels apart. That's why it shifts to higher and higher energy.
Thank you.
Other question? Okay.
You show a slide, they show the graphene bubbles. When you do the hydrogenation, only the bubble part ever hydrogenated. Other place, other region don't hydrogenate. Why? What's the mechanism?
Okay. Initially, the hydrogen goes everywhere. When the hydrogen first lands, it just lands as it is everywhere. But then you heat it up a little bit to overcome the diffusion barrier. The hydrogen will then find the most stable place to absorb. At about 300 degrees Celsius, the hum, it goes to the hum. The reason is this: the graphene that is flat interacts with the metal. You see, so it already interacted with the metal, it bonds with the metal. But the graphene that is not interacting with the metal, that is the bubble region. It is freestanding. So the hydrogen goes there. You see, the way the hydrogen bond is this. Once it bonds to one carbon atom, you generate a dangling bond on the other side. If you don't bond another hydrogen atom, it's not stable. So the best way to make a stable structure is one hydrogen here, up, and the other hydrogen inside. So it's a countersink. And the best place for this to happen will be the bubble, because one hydrogen here and one hydrogen there. The place where the graphene is attached to the metal is difficult to interact because it's already bonded with the metal. That's why it seems to be counterintuitive for people who think that hydrogen will go to the bottom region. But the bottom region has already bonded with the metal, so it goes to the free region that has not bonded to find the bonding partner. So it decorates all the bubble region.
Just to follow up this question, you mentioned there are pseudo-magnetic field induced, right?
Yeah.
Up to 680 Tesla?
Yes.
Can you also explain how, intuitively, how this magnetic field can be induced?
How this magnetic field? This is not a real magnetic field. This is just like there's a gauge field on the bubble. It's not a real magnetic field. We say there's a pseudo-magnetic field because the energy level is split to the Landau energy level.